Frequency is how many waves happen per second. The amplitude is the vertical distance from the midline to the peak of the wave. So in other words, some waves go up really high, really low, really high, really low. Those that have a high amplitude, those that have a smaller would have a smaller amplitude. Equation that we didn't cover too much in Chem 1 or in Chem 2 for that matter is V equals C divided by lambda, where C is the speed of light, 3 times 10 to the 8th. The lambda is going to be your wavelength, and the frequency is your velocity in this case. Planck's quantum theory, energy equals h times v, where h is Planck's constant. This is a number that would be given to you. So all you have to do is calculate energy by knowing the velocity. Granted, you might have to use the previous equation to first solve for velocity and then plug that in with the h. What this equation shows is the energy of a photon. So when light is given off, it can talk about how much energy is associated with that. One conversion that you'll probably need to know, wavelengths, since they're so small, are in nanometers. There's 10 to the 9th nanometers in 1 meter. So this conversion you'll probably need to know because the speed of light is given to you in meters per second, so your unit will be meter, but once again, wavelength typically in a nanometer. So that conversion would be helpful for you. Second equation you might have to be aware of is HV equals KE, which is kinetic energy, plus W, which W is work, something that we did talk about already in the thermodynamics unit. So not certain how many of these equations you'll need to work out. That's why I'm not doing a sample problem of these. The Bohr model of the atom is the next slide to go over. The Bohr model of the atom was based off of hydrogen. The idea that electrons can get excited and go from a ground state to an excited state, so they can jump energy levels. And when they fall back down, they give off different beams of light. The emission spectra or the bright line spectra are those bars of light they give off. On the bottom here, it might be a little hard to see. This is the bright line spectrum for hydrogen, though. So what we can do is we can calculate the energy associated with any of these bars, involving the equation on the next slide. The next slide gives you this very complicated equation, which we are going to be solving for. The only equation that we're solving for in this one. The RH is called the Rydberg constant, which once again would have to be given to you. Now defining N, you'll see an Ni for N initial and an Nf for N final. Usually lowercase n is moles. It is not that way in this one. N is referred to as the principal quantum number. So in other words, what was the initial energy level that the electron started at? What's the final energy level that the electron started at? Here's a question that we're going to solve. It says, what is the wavelength of a photon in nanometers emitted during a transition from the Ni5 state to the Nf2 state in a hydrogen atom? So we're going to go ahead and do this one on the board. This is where my cameraman turns the camera so we can see the board. I didn't have to do that with Matty Murphy at all. To begin with, we're going to use our equation, the RH part. So we are going to solve for, begin with RH, is the 2.18 times 10 to the negative 18th joules number. We are going to then multiply it by the 1 over Ni squared minus 1 over Nf squared. 1 over Ni, the initial, was 5 squared, minus the final, 2 squared. This is going to equal the HV, which the H value we already know. That was the constant given to you on the previous page. So that's the 6.63 times 10 to the negative 34th V. So now it's a matter of, okay, 1 divided by 25 minus 1 divided by 4, multiplied by this, divide by there. If I do all of that algebra, I end up with V equaling 6.9 times 10 to the 14th. This is the first thing to note. Granted, originally, you'd have a negative sign with that. All the negative sign refers to is that energy is given off, which should make sense. If you start at a higher energy level from the nucleus and you fall to a lower energy level, you are giving off energy. You are giving off light energy. So don't even worry about that negative sign. If you want to get rid of that for the rest of this, that's fine. The next equation we have to do is go back to the C over lambda. Lambda is our wavelength, so that's what we want to solve for. So here's lambda. It is going to equal V times C. So plug this into your equation then. of lambda equals, the V given to me is the 6.9 times 10 to the 14th speed of light. Oh, I'm sorry, I said this up wrong. If I wanted to solve for lambda, it would actually be c divided by v. So now, what I should do instead is take the speed of light, which is 3 times 10 to the 8th, divided by the v value that I had before, to the negative 14. This would give me a wavelength of 4.35 times 10 to the negative 7. My unit is meter though. So there's one more step I have to do to solve this problem. And the step that I have to do is I have to go from meters to nanometers. So if I show that very last step, my conversion is going to be 10 to the 9th nanometers over 1 meter. And if I do that, I end up with 435 as my nanometers. Visible light is from 400 to the 700 range for nanometers. So a good way to check your answer is, does this make sense? And the 400 range does make sense for this particular problem. So once again, all I did was plug into the top equation, which was given on the slide, where I had my 1 over my Ni, my 1 over my Nf, squared them both. That got me my velocity, or my frequency in this case. From there I can solve for lambda, gave that to me in meters, convert that into nanometers. That's the only calculation that was saw in this chapter. The rest of it is designating where are electrons located. So if we move on to the next slide is going to be on electron configuration. So to begin with, electron configuration shows the location of electrons. And what you do is you build up from hydrogen. So we know where hydrogen's designation is, and then we get further and further away from hydrogen, we get larger and larger and larger. The periodic table we can divide into energy levels and into orbitals. What we're going to do is give you an example of the electron configuration for selenium. The first thing I want to do before we do that, though, is I want to quickly go over the periodic table with you. So with the periodic table, energy levels start with the energy level of 1, then 2, 3, 4, 5, 6, 7. Pretty simple there. This is called the s orbital right here, these first two columns. The last 6 are called the p orbital. So since this is in the second row, this would be the 2p. This would be the 3p, 4p, 5p, 6p, 7p. The middle is the d orbital, and the d orbital is a little bit different, because even though this is in the 1, 2, 3, 4th row down, scandium is actually 3d, so the d jumps back one. So this is 4d, 5d, 6d. Finally, the f orbital is on the bottom. The f orbital is taken out of the d right here and actually jumps back 2 energy levels, so you have a 4f and a 5f right there. So that's all things that if you have your current periodic table, they give the shorthand notation directly underneath anyway, so it shouldn't be too tricky if you have that. But at the same time, you should in general know on a generic periodic table, energy levels, the d jumps back one, things of that nature, which the d is just the dip in the periodic table. So what we're going to do back on the board here is we're going to do the electron configuration for selenium. Selenium, if we start building up from hydrogen, starts as a 1s, and there's 2 electrons in there. The first one's where the hydrogen is, the second one where helium is. 2s2 would get me from lithium and beryllium. 2p6 would get me from the boron all the way to the neon. 3s2 would be the sodium and magnesium. I have to get all the way through 3p6, because that gets me to the argon. Next is 4s2, because that gets me through potassium and calcium. Then I jump back to 3d10, which is that first d block, and to get to selenium to end up, it's 4p4. So that's the electron configuration for selenium. The next thing we're going to show you is another way to represent electrons, referred to as orbital notation. Orbital notation shows the location of electrons plus the spin. This is something else that we covered in Chem 1. I'm going to give you the nitrogen example here in a second, but bring up the fact that there's 2 rules that we abide by when doing this. Pauli's exclusion principle refers to the fact that if you have two electrons in the same suborbital, they have opposite spin. One arrow's pointing up, one arrow's pointing down. Hund's rule says if you have multiple suborbitals, the electrons will fill each suborbital before they double up. So once again, we're going to show you on the board here the nitrogen orbital notation. Just like with hydrogen or selenium, we start from hydrogen and build up. There's a 1s. We draw an up arrow and a down arrow to represent the two electrons that nitrogen also has. Next is the 2s. There's an up arrow and a down arrow there as well. What makes 2p different is that there is 3 suborbitals within the 2p. Now, if you look at your periodic table, nitrogen is the third element in the p. So my first arrow goes up, my second arrow goes up, my third arrow goes up. I would not do an up and down and up because that would disobey Hund's rule. So that's one thing to keep in mind when we do this. This is the overall orbital notation for nitrogen. The very last thing that we have to cover then is what's referred to as quantum numbers. Quantum numbers is something we did not cover in Chem 1, and it's, if you know how to do electron configuration orbital notation though, you can do quantum numbers. There's 4 different quantum numbers. The first one is called the principal number n, which is referring to the energy level. So what is the last energy level that these things are in? That part shouldn't be too tricky for us. Second one's called the angular momentum. And again, it's referred to as the letter L. The name of the orbital, if you end in the s orbital, you're given a 0. The p is a 1, the d is a 2, and the f is a 3. The magnetic number can be varying based off of where the electron is located. If it's s, it can only be a 0. The p can be a -1, a 0, or a 1. And again, the d can be -2, -1, 0, 1, 2. I'll show you an example of that in a little bit. The final number is referred to as the electron spin. It can either be a +1/2 or a -1/2. And as I mentioned here, what we're going to do is go back to the board and show you examples for both of these. So, if I look at selenium and nitrogen, we're going to figure out what is the N number, what is the L, what is the ML, and then finally, what is the MS. Energy level is the first one. Selenium ends up at the very end occupying the 4th energy level. So that quantum number is just 4. L is the second one. L is referring to what orbital does it end with. And if you notice, it ends in the P. We designate that with a 1 for the L number. The next one is a little trickier, the magnetic number. What I'm going to do is show you the orbital notation for the very end of selenium. If there's 4 electrons, 1, 2, 3, 4, there's 3 possible quantum numbers for the P. 1, 0, and -1. The -1 would be this first suborbital, the 0 would be the second, the 1 would be the third. So the 0 is always designated as the middle of all the suborbitals. In this case, the last electron is in the very first, so we're going to call the ML number a -1. Lastly, the +1/2, -1/2 refers to the spin. If the last arrow is pointing up, it's a +1/2. If the last arrow is pointing down, it's a -1/2. In this case, -1/2. These are the 4 quantum numbers for the selenium problem. If I do the same thing for nitrogen, nitrogen ends in the 2nd energy level, so that's the first quantum number. The second quantum number is what orbital it is in. Remember, S is the 0 orbital, P is the 1 for the second one. The third one is where does the last electron lie? And here, once again, -1, 0, 1 means that the last electron is in the 1 spot. And then finally, the spin number, the last electron is pointing up, so that's a +1/2. Now again, if you have questions on the d orbital, if I just did a 1, 2, 3, 4, 5 for the d, if you look back on your note sheet, it says d can be a -2, -1. Well, if the electron ended here, it'd be a -2. This would be a -1. This would be the 0, the 1, the 2. Now we had you do electron configuration orbital notation in Chem 1 because that was a good way to just show where electrons are. This is by far the briefest way that we could show where electrons are using these 4 quantum numbers. And that is all we have for this chapter on quantum mechanics for chemistry AP review.